All right, so let's look at another example where we get a gas mixture after some reaction has taken place and how we can use the collection of over water or in water through water and using the concepts of dry and wet gas, we can determine the mass of a reactant. So in this case, we take potassium chlorate, KClO3, and we're told it was heated in a test tube, and from that, potassium chloride is produced and oxygen gas. And then it goes on to say, well, 0.65 liter of oxygen gas were collected underwater at 22 degrees Celsius, and it came to a total pressure of the gas that then was produced in the end came to 754 torr. We're also told that under these conditions, the vapor pressure of water is 21 torr. We're then asked to calculate the partial pressure of the gas, meaning the oxygen gas that is produced, and the mass of the salt originally present. Now, this initially might seem kind of weird because, right, they tell us that we produce 0.6 liter at 222 degrees Celsius, and it has a pressure of 754 torr. But we read because it is said collected underwater. This means this pressure that we measure there must be the pressure of oxygen gas plus the pressure of water vapor at 22 degrees Celsius. That gives us this total pressure. All right, this total pressure. Because remember, we have what we use, or the apparatus that we use to make these measurements, um, is kind of like, I don't know, like a box or a tube, kind of how they measure pressure using mercury. And this thing is filled with water. And on top of that, you usually have some kind of cylinder or another tube that you are able to measure the volume of, the pressure of, the distance, or anything like that, which is also filled with water. And then connected to that, you have a little rubber tubing, and this little rubber tubing is connected again to some kind of test tube apparatus in some manner. And in this test tube is your reactant. So in this case, it's your KClO3 there, and we're told we're heating it. So there we go. We have a little heating stand, heating mantle, or Bunsen burner. And because of the heating of this, there's gas given off. So let's make it purple. There's O2, so this is O2. And the O2 eventually bubbles up into here. But by it reducing the water level in this tube, it causes headspace. And the moment that we have headspace, it means we have O2 gas, as well as water vapor, so H2O gas as well, is then also present. So that means whatever pressure we measure here, so whatever our P measurement is there, is the sum of the oxygen gas and the water vapor pressure. Okay, so that's what we have. That's that 754 torr up here. Okay, so given that information, or this situation, that we understand what we're looking at, we're told that the vapor pressure is 21 torr at this temperature, and then we're asked to calculate the partial pressure of the oxygen gas and the mass of the salt initially. So the partial pressure one should be quite straightforward because we know P total is equal here to 754 torr, or millimeter mercury, whatever your poison of choice is, must be equal to the pressure, the partial pressures of the vapor plus the oxygen gas. So remember, this is the so-called wet gas. wet gas. Because it's water vapor, so it refers to as wet gas. So the question could also have said, what is the vapor, or what is the pressure of the dry gas? So this is the dry gas. Okay, oops. So you just quickly plug it in. We're told this value is 21 torr. So plug it in, therefore, the partial pressure of O2 is equal to 754 minus 21, so that's 733 torr. Right. And of course, you write nicely, the partial pressure of oxygen is that. Okay. Now we're also given some information. We know what the partial pressure of oxygen is. We know the volume of the oxygen is equal to 0.650 liter. We know the temperature of all these gases, 22 degrees Celsius, so that's 295.15 Kelvin. And of course, as always, once we know these three things about a gas, we can determine how much of the gas we have. And why is that relevant? Because we also want to know how much salt was originally present. And the best way, or the only way that we can really relate the salt and the oxygen gas at this moment is by saying 3 mole of oxygen is going to form for every 1 mole of KCl, or potassium chlorate, that we reacted or burnt. So in other words, if we can get the number of moles of oxygen that has actually been produced, we will be able to relate it back to the original mass of the salt. So you go ahead and you say the number of moles of oxygen. So maybe make a star for yourself here. Just quickly remind yourself that PV is equal to nRT. Therefore, N is equal to PV over RT. So this then is equal to the partial pressure of the oxygen multiplied by the volume over R and T. This is also the volume of the oxygen. Well, volume of the oxygen, volume of both of these gases will be the same because they're in the same space. So you can just call it V. It's actually just equal to V. And we plug in the values. So 733 torr multiplied by 0.650 liter. And our temperatures, as always, is in Kelvin. So 295.15 Kelvin. Question is, what does the units, or what is the value of R? And I think I have it here somewhere. There it is. So we're looking at the gas constants. So in this case, we're using torr and we're using liter. In other words, this would be a useful value to cancel with the liter and the torr. So our volume is in liter, our pressure is in torr, and we choose the correct R value according to that. So we use 62.36359 torr liter mole per Kelvin. Gives us a value of 2.59 times 10 to the power negative 2 mole oxygen. Okay. We know that now. We can use the chemical equation to relate the two species. So 1 mole of KClO3 will produce 3 mole of oxygen gas, right? That's what the chemical equation tells us. It's 1 to 3. We have 2.59 times 10 to the negative 2 mole oxygen gas. And therefore, we can calculate the number of moles of KCl3O3 that would have produced that. So we cross multiply and divide. cross multiply. This means that NKClO3 is going to be equal to 1 mole KClO3 produces 3 mole of O2. This is, of course, just written from the equation or from your multiplication. You can directly write that down, whichever is easier for you. And this needs to be multiplied by this 2.59 times 10 to the negative 2 mole oxygen. And now we check. We say, well, mole oxygen cancels with mole oxygen. We're left with a third mole KClO3. And that is going to be some value. You can just plug that in. So it's going to be something mole KClO3. Because I just want to, you should be able to do that by now. So then the mass of KClO3 is equal to the number of moles of KClO3 multiplied by its molar mass. All right, mass is equal to number of moles times molar mass. Molar mass of KClO3 is 122.6 gram per mole. And this value over here goes over there. And then you will get 2.12 gram KClO3. Okay, so that's how much salt was there initially, originally present. Okay, so that's the important thing that you always have. If you're working with a gas and you have pressure, volume, and temperature information, you can always determine how much of that gas there is. And of course, if you're dealing with a gas mixture, you need its partial pressure because it will occupy the same volume and have the same temperature as all the other gases in the mixture. Only its partial pressure is going to differ. So yeah, that is the important points. So we can always calculate the amount of a gas. You can always then use the reaction equations to determine something else of the system. And importantly, this idea of wet gas and dry gas. If you're collecting something over water or in water or anything that suggests this kind of apparatus setup that I drew here, then you have the concepts of the dry gases and the wet gas. And the wet gas always refers to the vapor pressure of the water at the given temperature at which the process or the reaction takes place. Okay, thank you for watching. I'll see you in the next video.